All right, so some reminders, our next exam is not going to be until the Monday of the last week we meet. So our final exam is August 1st, that's a Friday. The time is a little shifted, that one's gonna be at 2 p.m., not noon. But the third exam is going to be that Monday. I just didn't want to go back to back. I wanted to give us a full day of review for the final. And so I have Monday, third exam, Wednesday, review for the final, Friday coming for the final. Unit 3 is a little bit heftier than Unit 2. Unit 2 we only did in 2 weeks, whereas Unit 3 we're gonna do a full 3 weeks. So we'll have more information. I plan on having the Unit 3 homework, at least the first one, up today. And so if we take advantage of the more time we have for this upcoming exam, I recommend, getting the homework done as soon as possible. That's just gonna be, I'm always gonna push for that. If we cover gas loss today and you feel really comfortable with it, maybe work through some of the easier problems the second day or the day after. And then, if you get to hit harder problems, you can come and talk to me the day after or the class after, and we can get through those problems. But yeah, do what you can. I kind of had to manipulate myself because when I was much younger, I was a procrastinator. I didn't do anything on time. But now I had to tell myself, do this for future you. So do this for future you, get those homeworks out of the way. Your next quiz, I'm still gonna work on it, but it's not gonna be open until Friday. So at least you have a little time for the next quiz. Okay. Any questions about any of that? I will be giving back all of the exams. If you would like to see the key is up. I highly recommend going to the key and making sure I made sense. So is my math okay? So what I took off is, what I normally do is I take off the points in the bottom left-hand corner, and then I add them all up and subtract them from 100. So double check and make sure my math is okay. Double check and make sure that the key is relating to your stuff. Because what if the key says that you did it right and I took off points? So you want to definitely advocate for yourself. And then come and chat with me if I did anything. But I will warn you, sometimes students will advocate for themselves a little too much when nothing they did was right in the short answer. But I have no problem going over the short answer and saying, okay, and we have a discussion and say, okay, should I give more points back? But yeah, advocate for yourselves. Yeah, right now our Canvas site, I'm just going to repeat what was on the announcement. Our Canvas site has your 2 lowest quizzes dropped and your 2 lowest homeworks dropped. So if you get 100s on everything else, then your grade's going to be as accurate as possible. But if you end up having another drop later on, it'll keep populating and keep those drops. But my advice is do everything you can to get the easy stuff 100%, right? So homeworks, 100%. Quizzes, if you can, get 100% on them, because that's going to boost up those exam grades. I always use that to boost my exams. I'm not a very good exam taker, so it's a formative assignment, boost up the exam assignment. Yeah. Exams, though, I will say your lowest exam grade will be dropped. So the way that works is after your final, I work it in and I'll say, okay, if your final is higher than one of your 3 midterms, then the final exam will replace one of those midterms. So yes, you do have a drop exam coming. That's if the final is higher. If the final exam is not higher, then those 3 exam grades will count towards your overall. So I don't have a drop incorporated in your exam portion. So your grade might be a little lower or higher than we expect. So I'm just gonna put that out there. All right, let's get started. So verse applied to gas laws. If you are online, there is a worksheet we'll be doing later. So if you can download that and get that one ready. So it's a 3-page worksheet. We're gonna kind of break it up into 2. And then we're gonna have some little bit of downtime, I'm hoping. This is a pretty hefty PowerPoint. Typically it's given over 2 days, but technically 1 class is days. Let's review verse and then get into gas laws. I will be going back and forth between this and website, so just bear with me as I go back and forth. Up until now, we have hit 2 major problem solving techniques. We've hit dimensional analysis, which was the setup on how we were able to cancel out units and use conversions to go from one thing to another. What we've hit the most of dimensional analysis was when we're going from molecules to atoms or going to moles, things like that. So we're just gonna build off of that. All we do is dimensional analysis, but that dimensional analysis is the setup of how we go from one thing to another unit conversion. Yeah, stoichiometry too. We also hit on verse all the way back in unit 1. Verse is when we have an equation and I give you variables and you have to rearrange it and solve for what we're asking. So mathematical formula connects the variables you have with the variable you want, and then the verse steps you through solving the problem. So if you're very comfortable with verse, you don't have to break it down into all those steps. But even myself, when I do these problems, I always use verse. I know it seems very redundant because I can do all this pretty much very quickly in my calculator. But when I'm doing my own short answer portion of anything, I have to do verse to like prove myself right. So we're gonna keep practicing verse. Does anyone remember what verse stands for? What about the V? Yes. So the V in verse stands for variable, which is letters. So if I was to give you an equation with X, Y, and Z, X is this, Y is this, Z is this. If I say solve for Y, you can rearrange it using verse and solve for what I'm asking. So V is variable. What about E? This one you're sometimes given, but you might have to remember it on top of your head. Yes, equation. So like if I said X equals Y times Z, that would be the equation. I have letters there, we might have to rearrange it. So obviously that's not something you'll see for us because that's not an equation, but you will have to know an equation. Does anyone remember what R is? Yes, we're going to rearrange the equation to solve for what is missing or what we're looking for. So rearrange. S. Yes, this one includes 2 S's. It's substitute, meaning that you might need to convert units. So let's say an equation, if you remember, we did the Q equals MCAT equation a long time ago when we first did verse. You know, if the temperature I gave you was in a different unit, you would have to convert it to the unit that's after you. So that would be substitute, and then of course plug everything in and solve. And then lastly, this one I think we all kind of skip, especially when we have a limited amount of time in an exam. But this one is going to be evaluate. And you want to give yourself time to evaluate too, because I think all of us kind of like when we have a time, we kind of skip this step a little bit. But it's the purpose of this step is to say, does this make sense? Does my answer, my number, my answer, does it make sense? If I know that temperatures are between this number and this number, and I'm getting a temperature of 50,000, does that make sense? It might be there's a calculation error. Maybe there is a mathematical algebra error with the rearrange. So if we kind of know what our ranges should be, we can figure out, okay, I made a mistake and we can go back and fix it. This is something I think I developed later on after I got more comfortable with chemistry, but it saved me so much. Even in my lectures, I'm looking at my math and I'm saying, that doesn't make sense. Let's go back and fix it, which is okay. So we always want to evaluate before we submit an exam or an answer. Applying verse to a new topic. So we definitely already hit, because we did use one of these equations already, but we're going to actually talk about the theory with that equation now, because remember, I can give you any equation and you can use verse. So if I give you X equals Y, Z, and I said Z is this, Y is this, but you can still use verse. So we have already saw one of the equations, but now, like I said, we're going to go into all of the details about why it works. So we're going to treat the new problem as a math word problem that you will tackle with verse. And then pro tip, make sure all of the units are compatible. So sometimes if there is no set unit, meaning that if you have it in milliliters, you can leave it in milliliters. You have it in atmospheres, you can leave it in atmospheres, but you need to be consistent when you're dealing with units. So always, and I'll tell you now on verse, I think I don't take off a lot of points, but I definitely do take off points if students don't include units, if it's a short answer problem. Always include your units. I just want to hone that in right now because you can catch your mistakes if you include your units. So keep them in. And then you can solve anything with any equation this way using verse. I can give you any equation and you can solve it. But we're going to get into what is gas. We're going to, this whole section is all about gas. And going back to states of matter. So macroscopically, let's say if we talk about the water cycle, we can see the water cycle. We can see water going from a solid to a liquid by having ice melt. We can see water going from a liquid to gas by boiling it on a stove. We can see it going from a gas to a liquid by having condensation, which I have on outside my Stanley right now. It was a gas and now it's a liquid. And then going, you know, you can have it freeze and things like that. So macroscopically, we can see what is happening. The picture shows what's happening microscopically. So I'm seeing those particles through a microscope. So solids hold their shape really well. They are gonna, you know, the colder it is, if you see the temperature, the colder it is, you can get it to anything to come into a solid state. So gases, like right now, most of our air is nitrogen. But if I get our room to a cold enough state, I can turn this gas into a liquid and into a solid. It just needs to be cold enough. Or if I heat something, if I heat, let's say this table to a high enough temperature, I can get this table to go from a solid to a liquid. It would have to be extremely high, but same concept. Things can go from a solid, liquid, and gas, and vice versa. There is a such thing under perfect conditions where we could go from a solid directly to a gas. That would be sublimation. That would be like if I go get dry ice from the grocery store, it's carbon dioxide. They cooled it to very low temperatures, taking CO2 and turning into a solid. But at room temperature, it instantly turns into a liquid. It doesn't even, sorry, gas. It doesn't even turn to a liquid. So that's sublimation. And then the opposite of that would be deposition. That's under very specific temperatures and pressures. So symbolically, we've already also hit on that. That's if I was to take, let's say these are all water molecules. It would be including the equations with those phases. So it's really good to think about this in all those three scales. Macroscopically, thinking the water cycle and what we can visualize. Microscopically, what's happening here. So that solid being very nice and structured. And then liquids are more fluid. So they do have a little bit of hold to them. Where gases, once you have it in the gaseous form, it's not holding anything together. It's free flowing. It fills the container. There's nothing holding these atoms together. So microscopically, we can see the difference, and then symbolically would be just showing the chemical equations. How do gas particles move? So it's important to kind of know these details because this is all about the kinetic molecular theory. So gas particles, like going back here, these are gas particles. They're free flowing. They fill the space. They're continuously in motion in straight lines at a variety of speeds. If I had a gas in an unlimited open air, let's say it's outside, and I had one gas particle floating, it would go in a straight line until it hits something. Eventually it might hit something and then it'll bounce off and go in the other direction. The smaller the volume, let's say we go from outside to in this room, you're more likely to hit something. So the gas molecules would hit our walls and come back over. And if I go into an even smaller container, let's say my Stanley cup, even quicker when I hit the container and move on. So they move in straight lines at a variety of speeds. A lot of things can decide that, and it hits the walls and it keeps moving. These particles are tiny. Majority of the things in between these particles is going to be space because they're so small. The bigger your space, like let's say I'm outside versus in this room, the more space between those particles. The smaller it, the less space, but there's always going to be majority space in between those particles. So most of the volume of a gas is just going to be empty space in between those particles. They don't have charges. So when we think of gases, I know we've talked about ions a lot in Unit 2. None of those ions, those are all aqueous ions. These are gas particles that are not ions. They are neutral, so they do not repel each other. So if I have two molecules coming together, they collide and bounce off each other, but they're not repelling each other and they're not attracting each other. They just collide. Energy is conserved when particles collide. So that energy is conserved, it does produce some energy, and it keeps happening. Particles on average will move faster at higher temperatures. This is kind of the same for everything. When temperatures are increased, those particles will move in a faster direction or just faster in general, and then they will have more collisions. More collisions also will increase that temperature. These are known as the kinetic molecular theory of an ideal gas. You want to kind of think about what's happening in the gas mode. It'll help remember things. But I'm going to switch over to the link on the next slide and talk about this together. Let's share. And then I want to go here. All right. If you want to know where this is, if you go to the very next slide, it has this link. This is a PhET simulation, which I love PhET simulations. They're from Colorado. I forget what university in Colorado, but this will help us visualize what is happening in the gas. It looks very confusing. I did play around with it a lot before coming in. But yeah, let's say we have, this is a container. Is this container open or closed? So if you look at all four walls, this would be an example of a closed container because, you know, I would have to open it. Sorry, I'm like looking at the wrong thing. I'm like looking at the, here's how I can open that container. So the gas particles will fill any container. So this is how you add the gas particles. And it'll expand, so they're all going in a straight line until it hits something. It could be another particle, it could be the walls, but the gas will expand and keep moving, collide, keep going, collide it, and then keep going. Look at this pressure gauge. If I increase more particles, that means that there's more collision, either with the walls or with other particles. So that pressure will go up. Temperature. If I cool this gas, the colder it is, the slower those particles move. The higher I go, the more collisions will happen. The speed of these particles will increase. It's getting faster and faster and faster. Also note, as I increase my temperature here, this pressure gauge is going up, and then it decreased as I cooled. So there's a lot that happens when you deal with gases. I can set certain things constant and see what happens, or I can just leave it at nothing. I'm holding nothing constant. I'm just seeing what is happening to everything. Temperature and pressure look like they go up with each other and down with each other. I can also play around with the volume. So I just increased my volume and the pressure decreased. So I can see that that's kind of inversely. If I increase my volume, my pressure, look at that. Oh, my lid came off. Yeah. Also, like if I take the lid off, you can see how those gas particles will fill a space. If that space is not closed, they'll all get them. They'll go find more and more space. They like to fill whatever container they are in. I'm gonna just count collisions. So I did one pump, not a lot of gas. So the collisions, yes, there are collisions, but let's try it again if I was to put a lot of gas in there. You can see the more gas particles in there, the more collisions. If I reset this, let's do just one pump and count collisions. If I cool it, there's fewer collisions than when I heat it. And that is all because the more speed, the more temperature, the more collisions. We can also hold things constant. So over here, this is a lot of fun to play with because gas, there's a lot of things we think about when we think of gas. One, volume. When I think volume, I'm like, okay, if I put gas in a balloon, let's say I put 1 mole of something in a balloon, what's going to happen to volume if I cool it or heat it? So I'm going to, I guess I'm going to hold the pressure constant. Hold the pressure constant. And I want to think about what happens to the volume as I cool it. Oh, so. So if I hold the pressure constant and I cool my gas, where the volume can definitely change, it's not a set environment, it'll reduce with temperature cooling. So it'll come closer together. It's the opposite if I heat it up. If the volume can move around and I heat up a gas, it'll expand. The way that I relate this to something we can all visualize is our tires. What do our tires do in the summers versus the winters? So we fill our tires up with gas. And when it's really, really cold outside, typically our tires will decrease in size because rubber does expand, not a lot, but it does expand and decrease. So our tires will deflate in the winters where sometimes we have to add a little bit of air pressure gas back in. In the summers, if you don't not careful, your tires can expand and sometimes get a little bit too much pressure and potentially pop. So that's a great example of this concept with our tires. If I was to like hold, let's say, our volume, okay, so I want to look at the pressure. No, we're holding pressure constant. So that means temperature will change. So if I decrease my, so it's 182, yeah. So if I keep my pressure the same and I just change my volume, look at the thermometer. As volume increases, your temperature increases, and as volume decreases, your temperature will decrease. So that they're kind of comparing each other. If I keep my volume constant and I change my temperature, so if I heat it up, look at the pressure. The pressure increases with the temperature and the pressure will decrease as you cool it. So this is really helpful as we go through the next concepts that if you're kind of confused by anything, I highly recommend getting that simulation up and running to maybe visualize and see what's going on when you start making these changes. But yeah, this is a lot of fun. Right. I do want to point out that on the next slides, I'm going to kind of go through the next slides real quick. Instead of me having a blank slide to talk about it, let's talk about it while it's in front of us. That's what I think works best for me, at least. But we need to think about the kinetic molecular theory about why a gas will expand to fill its container. Why? Gases are very lightweight, and they're already, they hit their boiling point and they're in that gaseous phase. The reason why they fill the container is because there's no bonds or holding them together to make it come back to a liquid or a solid. So they will always expand to fill the container. And then we need to use the kinetic molecular theory to explain why a sample of gas can be compressed to a much smaller volume. So if I was to have this filled with a lot of gas, no matter how much gas I put in here, I can still play around with these volumes because it will expand to fill a container. There's no limit. If this was a liquid, I can play around with volume while I want. The liquid's going to be the same volume. Same with solids. I can put it in a balloon, but it's still gonna, the balloon, it doesn't matter. But with gases, yes, I can decrease the volume and increase my volume. But the gas particles will always be able to free flow and move, and then it'll hit the sides of the container and keep moving. The volume definitely has something to do with pressure. You can see that there's a lot more space in between those particles as volume increases, whereas look how little space it is as the volume decreases. So the question is, use the kinetic molecular theory to explain why a sample of gas can be compressed to a much smaller volume, and that is because of all of that space between each individual gas particle. So there's always going to be space, and majority of it going to be space. And so because of that, I can play around with the volume. The next question for discussion questions was use the kinetic molecular theory to explain how the motion of particles produces pressure. So you can see whether I'm dealing with volume or not. So look at the pressure up here. You know, pressure is decreasing as I'm increasing my volume, so they're inversely proportional. And pressure is increasing as I decrease my volume. So that pressure goes up a lot. I can also play with ground pressure by using heat. My pressure will increase as I heat everything up because more collisions means more pressure. So more collisions with other particles, more collisions with the volume and surrounding. So I had so many collisions I popped. If this was a balloon, I just popped the balloon. If you heat a balloon enough, it will pop. I'm gonna close and show you if I cool it. Same thing if I cool it down a lot, the pressure will. So it means less collision, and that is why the pressure is less. So collisions, pressure, yeah, so more collisions, more pressure, less collisions, less pressure. Those collisions exert a force, and that's why there's pressure. If anyone has a question, please just blurt out. I don't want to be skipping through things if it's still confusing. All right, so I'm going to go back to our PowerPoint slide. What I did was I kind of talked on the next several slides. They had discussion questions. So here is where you can find that PhET simulation. It's on the very next slide. I asked these questions and we talked about it. Same with these discussion questions. So I'm going to skip to here because we kind of hit on the other slides. So gases are well described by a lot of different closely related math equations, both macroscopically and symbolically. We've hit on using the ideal gas law equation and other equations like the Q equals MCAS equation. They all deal with gases. Our objectives for this section include identifying what properties of a gas we measure and converting their units to what we need. So we measure pressure, volume, temperature, and amount. The amount of gas will affect it. If you have more particles in there, there's more collision. Less particles, less collision. So identifying what are we measuring, and of course, if we have to convert the units, we need to be able to. And then qualitative relationships such as Boyle's law, Charles' law, and Avogadro's law. All of these kind of talk about pressure, volume, amount, and temperature. They kind of relate it, and then sometimes they'll keep something constant and focus on the other two. And then numerical relationships such as combined gas law and the ideal gas law. So we're kind of relating all of that in. One second. All right. So on the PhET simulation, we definitely played around with pressure. We played around with volume, and we did play around with the amount. That's what I was doing is if I did one pump or if I did a lot of pumps. So the more gases versus a less amount of gas. And then we definitely played around with temperature. So all of those will affect gas, and we can measure it with the gas. You want to get comfortable recognizing these variables. So going back to verse, P is for pressure, V is for volume, N is for amount. Typically it's in moles, and temperature is capital T. So if I was to give you an equation, you want to be able to relate, okay, this is what those variables stand for. pressure. How does the motion of gas particles exert pressure? So even if I'm not changing, let's say I have a piston and I have an open, set volume and I have a piston above it that I can play around with the volume. If I'm not changing physically the volume, I can still affect pressure by doing other things, such as increasing my temperature. There are other, or increasing my amount of things in there, so I can keep adding more molecules. So there are many ways to increase pressure if I was to not play around with volume. The way that that works is you can increase or decrease your pressure by increasing or decreasing the amount of collisions. That could be using volume, temperature, or amount, but it's all about the collisions. Each collision exerts a force, a very small amount of force, but if you have enough of them, it will affect the overall pressure. Does that make sense? How do we measure pressure? Typically, we always kind of assume that our atmosphere right now, because ATM represents atmospheres. I think on average, the Earth's like around 1 atmosphere. So this room, we always kind of make an assumption and say, okay, in an ideal world, we're at 1 atmosphere. But that does change because let's say if I'm up on a mountain versus if I'm like maybe in Death Valley, one of the lowest places on Earth, yes, pressure will change. Okay, let me see if I can remember. Altitude does affect pressure. So as I get higher up in the air, how does that affect? Does anyone know how that affects pressure? So the higher the altitude, the lower the pressure, right? But versus, let's say if I go diving, if I want to like go under the sea, the lower I go, the more pressure. So higher, less pressure, lower. But yeah, so atmospheres, ATM is kind of like what we kind of describe Earth atmosphere as. So there's also PSI. I don't know what it stands for, but PSI is probably one very, very common when we deal with pressures. But for us as chemists, you'll see these most. You'll see atmospheres to represent, of course, ATM, torr, and that mmHg is millimeters per mercury. So we'll give you a number and give you a unit. And then you need to remember these conversions. I need to check and see if I give these conversions. I believe I would, but if I was to give you these conversion factors, can you do conversion? So this goes back to dimensional analysis. You set up your equivalents and then you use dimensional analysis to go from one thing to another. And we're going to practice that. The pressure at the center of a hurricane can be about 675 torr. How much is this in millimeters per mercury and ATM? So we need to remember that 1 ATM equals 760 torr, or 760 millimeters mercury. And 1 millimeter mercury equals 1 torr. So dimensional analysis is you have your given, which is 675 torr. And then you want your 1 on top. So let's do millimeters per mercury first. Sorry, wrong units. So we've started dimensional analysis using completely different units, but it's the same concept here. It's a conversion. So you just got to make sure that your units cancel and you're left with what you're focusing on the top. So given times 1 over given in units, and then that's going to be your answer. If I wanted to go from torr to atmospheres, I would have to use different numbers. I'll leave the one torr on the bottom. If I need to change those goes on the top. Those that, oh no, I don't. 760 torr, 1 atmosphere. So my units cancel and I'm left with atmospheres. How about y'all do the next one? So diamonds can be created by heating carbon and exerting 50 atmospheres of pressure on it. How much is this in millimeters per mercury and torr? So both.
So the center of a hurricane in like quite vacuum.
Yeah. Yeah, hurricanes are all about pressure differences because I'm not a weather person, but it's fascinating how pressure can affect things. I know with me, I can feel pressure in my knees. And arthritis is killing me. But like pressure affects tornadoes, hurricanes. Like I'm sure that was a big issue with what we had to deal with this past weekend with all of that. I'm sure there was a pressure change created that giant wall of rain. So yeah. With hurricanes, it's pressure and temperature because the perfect set of like ideal circumstances will create a hurricane. Okay, so if I want to set this up, what am I going to start with?
Um,
So you want to start with your given, which means that what I want is on top and what I'm given on the bottom. So let's start with millimeters per mercury. All right, so when I did this math, I got a very big number, so I'm going to simplify by using scientific notation. So my atmosphere, double check your units, my atmospheres will cancel and I'm left with millimeters per mercury. And you should get the same answer for torr because 1 millimeter mercury equals the same for torr. Is everyone able to set that one up? So these are not so bad. These are just unit conversions. We do this a lot. As long as you have the equivalent in front of you, or sometimes you can create equivalent. But if you have that, you can always kind of use dimensional analysis to set that up. Eventually, you might have to do it in several different steps as chemistry gets more complicated, but it all comes back to this, going from one thing to another. Volume. So volume is typically going to be given to you in milliliters or liters. Those are the most popular. Volume's rarely, I feel like if you're in a different field, let's say if you are in the healthcare field, they use cc's. You hear cc's a lot for volume, and that's just the same thing as milliliters. So 1 cc is 1 milliliter. But for chemistry, we always use the conversion of 1,000 milliliters equals 1 liter. And you have to be able to convert between them. So if I give you in liters and I ask for milliliters, can you do it? If I give it to you in milliliters and ask for liters, can you do it? So the equivalent that I'm telling you now, you will never be given this equivalent, but that goes back to knowing those prefixes. So milli, meaning 1,000, versus the SI unit. So the SI unit would be liter, and there's 1,000 milliliters in 1 liter. A chemical reaction between acetic acid and sodium hydrogen carbonate generated 27.6 milliliters of carbon dioxide gas. How much is this in liters? So I have to bring up and make that equivalent, that 1,000 milliliters equals 1 liter. So it's the same dimensional analysis. You start with what you're given and you convert it into what you want. So 27.6 milliliters times 1 liter divided by 1,000. As you get more comfortable with the basic math, if you are dividing anything by 1,000, you're just moving the decimal place over 3 times. So sometimes you'll get to a point where you can start doing this in your head, but there's no worries if you can't. So that'll be 0.0276. But if you can, sometimes you can kind of skip this step if you can just move the decimal place over. So if I multiply it by 1,000, I move the decimal place over to the right 3 places. If I divide it, I move the decimal place over to the left 3 places. Or you're always going to have the calculator, just divide it by 1,000 in your calculator. I think out of all of these, this is probably the simplest because I think I'm only going to give you something with liters in it. The other ones might be a little more complicated with those equivalents. Amount, moles. First, when you see these types of equations, moles is going to be a lowercase n as the variable. You want to get very comfortable saying lowercase n and thinking moles. Moles, let's just go back to unit 2. A mole is an amount. So if I had, let's say gold, if I had 6.02 times 10 to the 23rd atoms of gold, that's equivalent to 1 mole. It's just counting the amount of a very large amount of atoms. So if you need to go from atoms to moles, and most importantly, you'll see grams, a weight of moles, you need to use the molecular weight. So molecular weight, you go to the periodic table of elements and you find the molecular weight. So you might have to go between moles and grams using molecular weight. You won't always be given molecular weight. You have to be able to calculate it if I was to give you a question about it. So how do you convert from grams to moles? Using molecular weight. So if I have grams of something and I want to convert it to moles of something, I would have to take the molecular weight and flip it upside down. That way those grams will cancel and I'll be left with. If I need to go from moles to grams, I would do the opposite. I would take my moles of some substance and multiply it by the molecular weight to get grams. Let's put it into practice. Convert 777 grams of propane to moles. So we need the molecular weight for this to happen. What is propane? Yes. If I have C3H8, I have to calculate the molecular weight. There are 12, not 12. There are 3 carbons. And if I go to the periodic table of elements, each of those carbons has a weight of 12.01. And I have 8 hydrogens. And if I go there, each of those hydrogens is 1.008. And so if I was to Google it, you get 44.01 grams per mole. But you still need to be able to calculate this on your own. I'm not going to give you the molecular weight. And then as you go throughout chemistry, you're less likely to be given molecular weight. I'm very nice if it's a very large number. Like if I give you a very, very extensive thing, or if I don't feel like writing out the chemical formula, I'll just say, here's the molecular weight. But as we're learning, you're not going to be given it. So we're going to get more and more comfortable. So start with your given 777 grams of C3H8. And I want my grams to cancel. So I'm going to take the 44.01 and put that on the bottom. And I'll put the, the mole will go on top. type this into your calculator and double check my math. I did my math before coming in, but I might have made mistakes. So please check my math. This is also why it's going to be very important for y'all to use your units when you do this dimension analysis, because you see this a lot of the time where students will take the grams and multiply it by the molecular weight. So if you did that, your units in the very end would be grams times grams. It wouldn't be moles. So by us writing out those units, I can say, okay, well, my grams cancel and I'm left with moles, and it'll save me a math error later on. Moles typically are smaller than grams, because mole is a very big number, but it ends up being a very small. That's moles, so lowercase n. If I was have to do temperature, the units are going to be in Kelvin, and this is going to be on always when we're dealing with gases. You want to convert everything into Kelvin. I'm not mean, so I'll never give you something in Fahrenheit because I don't care about the Fahrenheit conversion. In chemistry, we typically will give you in Celsius. So no matter what I give you in Celsius, if you need to convert it to Kelvin, Kelvin is the SI unit, but Celsius is just easier for us to measure in lab. You just take whatever Celsius and then plus 273.15, and that gives you the temperature in Kelvin. So always convert to Kelvin when you're dealing with temperature of gases. Water boils at 100 degrees Celsius, convert it to Kelvin. So 100 degrees Celsius plus 273.15 equals 373.15. So just take your Celsius and add it. If I have to go backwards, go from Kelvin to Celsius, what do I now have to do? Yes, you have to do the opposite math. So if to go forward, to go from Celsius to Kelvin, I have to add. To go from Kelvin to Celsius, I subtract. So so this one, the boiling point of helium is 4.22 Kelvin. If I subtract 273.15, I now have degrees Celsius, and that's a very low number. So helium, that's a great question. So let's visualize what's happening. If I was to like have water is a solid when it's under 0 degrees Celsius. At our room temperature, water is going to be a liquid. Gases like helium and hydrogen and oxygen at room temperature, so at our temperature right now, they're going to be gases. They're already in the boiling state, in the steam state, if I was to compare it to water. So for me to get that, so at the same temperature as water, to get it to go all the way into a solid, I need to get it to even colder temperatures. So the boiling point going between a liquid and a gas, for a gas, like something like helium, has to be in such cold temperatures for that to happen. Because at our temperature, right now, it's happy as a gas form. So yeah, solids typically that are happy at room temperature is like the opposite direction. You need to get it to very high temperatures to get it to turn to a gas, where these are already gases at very low temperatures. So very opposite. So it's like a visualization. But everything's comparative. Like the cycle going solid to gases with whatever I'm comparing, it's all the same. So if I was to compare helium gas to gold, it's the same, going from a solid to a liquid to a gas. It just happens at different temperatures. So gold, if I want to get gold to go, I would get it to go to the gas form. It would have to be extremely high temperatures. Maybe if I throw it into the sun, I could get gold to turn to gas. But maybe on Earth, I can get gold to liquefy, turn to a liquid. So it's the same concept. Let's connect everything. So gas laws, there are gonna be several gas laws because back in the day, actually, let's come back to this. It's 12:50, let's come back at 12:55 and continue, but let's take a little mental break. Recording in progress. All right, let's connect all those dots. So moving on, gas laws. So we're going to start relating how pressure, volume, amount, and temperature will affect gas sample. There's two different approaches. There's the qualitative approach. So if one variable increases or decreases, what happens to the other variable? So I already kind of related this to our car tires. The two things that I'm comparing are temperature and volume. So if I was to heat a car tire up, the volume, what do y'all think? Does it increase or decrease? If I heat a tire up, what happens to volume? It should increase, so it expands, right? Versus if I decrease the temperature, let's say it's negative 20 degrees Celsius, it'll decrease volume. So we're going to start relating two things to each other. So you want to kind of think of it, if you can, macroscopically or microscopically. If you can visualize what's going on, it might help you remember the theory a little bit better. So that's qualitative. Quantitative is once you can start visualizing what's going on macroscopically and microscopically, if I give you numbers and I say, okay, well, if this is the number of the temperature here, what do you expect is going to happen to the volume here? So we can start calculating it based on those two things. But my advice is you want to get more comfortable with the qualitative approach because then it'll make sense with your numbers later. Numbers and math will always back you up. It will always back you up if you do everything correctly. But this is kind of saying, okay, well, if I know what to expect, I can catch my mistakes and double check and make sure everything looks good. So I want to be comfortable with both. So Boyle's law, this is qualitative. It's going to compare pressure and volume, and they are inversely proportional. The way that I like to think about this is if I have, let's say, a piston of gas right here. I have a canister of gas, and then on top of that gas, I have a piston that can push up and down on it. You can say, let's say I have a balloon in here, and I push up and down that balloon. If I was to push down on a balloon in an area, it'll increase my pressure. Sorry, yeah, I'm increasing my pressure, but my volume is opposite. So when it says inversely proportional, we'll sometimes use this little fishy, because if you do that, it means proportional too. But inversely proportional means they're opposite of each other. So if I push down with that piston, I am increasing my pressure, but I'm decreasing my volume because it's getting smaller. Versus if I release that piston, I'm decreasing my pressure and increasing my volume. They're inversely proportional. So sometimes I'll do this with myself, is I will say, okay, my pressure, if I increase it, my volume is the opposite, it'll decrease. Or if I decrease my pressure, my volume will increase. I'll kind of do that to help me visualize what's going on. But if you can think macroscopically what's going on, that might also help. I'm going to switch over to a video to show you what I mean.
In a demonstration of Boyle's law, looks like a vacuum bell jar. We'll apply a vacuum, basically pump out the air in the bell jar. The pressure outside the balloon will be greater than pressure inside. The balloon expands, trying and equalize the pressure. Volume and pressure are inversely related to each other. When we release the vacuum, the pressure increases and the volume decreases. As another demonstration of Boyle's law, we will put a marshmallow piece into our vacuum jar. The marshmallow contains air trapped in a mixture of gelatin and sugar. As we apply the vacuum, the pressure outside is lower than the pressure inside. The air in the piece will expand, trying to equalize the pressure. When we release the vacuum, the pressure increases and the volume decreases. As another illustration of Boyle's law, we will put some shaving cream into our vacuum jar. The shaving cream contains air trapped in a soap mixture. As we apply a vacuum, the pressure outside is lower than the pressure inside. The shaving cream will expand to try and equalize the pressure. As you decrease the pressure, the volume increases.
So what I like about this is that you can't always visualize what's going on with pressure. I can't look at that video and say, okay, I can see the pressure, but I can I can see what's happening with the volume. And if I know that they're inversely proportional, I'm seeing the volume of that balloon increase, I know the pressure has the exact opposite. So this was at a time where we didn't have all the answers, and so these people were kind of using the resources they had available in the 1700s, 1800s, kind of related to. They would try to keep the other two things constant. They would keep the temperature of the room constant. They wouldn't play around with temperature. They would keep the amount in the balloon constant, and they would just play around with what's happening with volume and pressure to compare it. But that's a great tool to visualize what's happening when you're comparing those two things. Back to my slide. The equation that Boyle came up with was, remember that pressure and volume are inversely proportional. So P1, V1 equals P2, V2. So in these types of problems, you're going to be typically given two pressures or two volumes, and then one thing will be missing, and you're going to be asked to solve for it. The ones and the twos, it doesn't matter what you correlate it to what number, as long as you're consistent to the before and the after. So I always will kind of say the ones are the initials, and then the twos will belong to the final. So before and after, meaning that, you know, this situation's at this volume and this pressure, and then if I change the volume of this, what is the new pressure? So you're given 3 out of the 4 things, and you're asked to solve for it. So it's how you kind of set this up. I want to point out that if both pressures are the same units, that's okay. You don't have to do any conversions. If they're different units, you'll have to make sure they have the same unit. And the volume's the same concept. So if they're both in milliliters, keep them in milliliters. If they're both in liters, keep them in liters. But if you have 1 milliliters, 1 liters, you need to make sure that they're consistent. That's very important when you deal with these types of problems, because if they're consistent, those units will cancel out. I like this next step because this is kind of using the qualitative approach. They are inversely proportional. So if I was to increase my volume and double my volume, I should half my pressure because they're inversely proportional. This kind of can also relate to the math. If you know they're inversely proportional and volume's going up, but your calculator is giving you a higher pressure, we made a math mistake and we can go back and fix it. So we want to make sure that we can remember this when we do this, to help us, you know, quantitatively be able to answer these problems. So they're inversely proportional. As pressure goes up, volume goes down, and as pressure goes down, volume goes up. So that the volume is doubled, then the pressure is cut in half. Whatever you do to the volume, you know, inversely proportional. If the volume is cut in half, then the pressure is doubled. So whatever, you know, opposite happening. All right. The pressure exerted on a gas sample inside of a syringe is tripled. So the pressure is tripled. What do you think is happening with the volume? So let's think about this. I'm going to do this in 2 different ways. Qualitatively, what's happening, and then quantitatively, let's put numbers in. But qualitatively, if I triple the pressure, what should the volume do? Decrease. It should decrease, but how much? What number? 1/3. So it's the opposite. So if my pressure is increased by 3, my volume is decreased by 3. So it should be 1/3. Let's have the math back us up. Let's assign numbers. I always will do this because I don't trust my brain sometimes, and I love to just have my math prove me right. So if, let's assign atmospheres. If P1, we do P1, V1 equals P2, V2. Let's say P1 is 1 atmosphere. If I triple my pressure, that means I just take that 1 and multiply it by 3. and I have 3 atmospheres. Let's keep our numbers incredibly simple and say volume 1 is 1 liter. What is volume 2? So all you have to do is kind of set up this problem and solve for V2 here. So y'all set that up and let me know what you think. I'm gonna write my notes underneath this, so kind of like ignore this right now. So that's 1 atmosphere times 1 liter equals 3 atmospheres times question mark. You can either rearrange the problem and solve and just have V2 equal. You can have it kind of set up like what I have on the left here, or you can just plug in numbers and solve for what's missing. But your question mark or V2 is just going to be 1/3. So we quantitatively were able to say, okay, if I triple my volume, my pressure, I will reduce by 1/3 my volume. But sorry, that's qualitatively. Quantitatively, you can always put numbers in there. Even if the problem does not give you numbers, you can still have numbers that make sense to the problem and use the quantitative way to answer. So both ways will give you the right answer if you forget one way. But can you see how I was able to come up with numbers based on the problem, even though it didn't give me numbers? Let's do number 2. Now they're going to give me numbers. And I'll let you answer that. The volume of a gas is changed from 15 milliliters to 60 milliliters. If the pressure was originally 400 torr, what is the new pressure? They're not telling you the pressure has to be in a specific number. So as long as the units are consistent, milliliters to milliliters, torr to torr, you don't have to do any conversions. So if you don't know how to get started, always do first variables, equation, which I have up here. This is the E inverse. Rearrange, substitute and solve, and then evaluate. Make sure you also assign those variables correctly. Your before needs to be the 1s, your after the 2s. So the 15 is V1, the 60 is V2. It says the original pressure was 400 torr, that'll be P1. If it said the final pressure was 400 torr, that would be P2. So use those words in the problem to help assign the variables. We are looking for P2. So when I plug everything in, first, before I plug everything in, what's happening to the volume? Is it increasing or decreasing? It's increasing, yeah, going from 15 to 60. What should happen to the pressure? It should decrease. If my math proves me incorrect, I made a math mistake. So your pressure for P2 needs to be smaller. So when I type that in, I get 100, yeah. Yes. The math will always back you up, but it's really good to have that qualitative understanding before you plug everything in, to kind of know what do you expect, because if I know what to expect, I can catch those mistakes. And sometimes if you're given a multiple choice question, you can eliminate answer options. You can say, well, you should decrease. So I can go in and eliminate all the ones that are increasing. It could save you on an exam. And then you could, make an educated guess. You don't know how to do it. If you don't have this equation memorized or in front of you. How does that feel? Charles Law, this is a completely different scientist. He went off in a different direction. He compared volume and temperature. So he kept pressure the same, and he kept the amount the same, and he just focused on what's happening temperature-wise and volume-wise. So volume is directly proportional to temperature. So if I increase my volume, my temperature should also be increasing. If I decrease my volume, my temperature should also be decreasing. So this is you're thinking about your tires. So if you are like, wherever would have think of it, I forgot how it goes, just think about your tires in the winter versus the summer. I'm going to switch over to that video. I'm just going to.
Well, the rubber gets kind of brittle. Sometimes it's sort of thin. You probably see better than where you're sitting.
What he's doing here is he kind of took a glove and blew it up with his breath. So he has just, carbon dioxide. Let's say it's just pure carbon dioxide, a little bit glove. What he's pouring on there right now is liquid nitrogen. Nitrogen at room temperature is in the gaseous phase. But if you cool nitrogen down very, very much, so really, really low temperatures, like, I don't know, negative 70 degrees Celsius, nitrogen will turn into a liquid. So he's pouring a very, very cold substance over that balloon of gas. So remember, volume and temperature proportional. So if I'm pouring it very, very cold, my volume should be doing the same thing, decreasing with the cold temperature. And then as it comes back to room temperature, the volume will go up. So sorry for not explaining. So you can see that glove is decreasing as it's in a very cold chamber. But the second he pulls it into that chamber and it's back at room temperature, look what's happening.
According to Charles Ross, it's great.
Look how small.
Much air in there was before, but all you had.
Look at the glove.
And if you look. Like, show this on the camera. If you look under the camera there, you might be able to see down here. I can see it quite clearly, but I don't show up on the camera. We've actually managed to liquefy some of the air. The faders as well. Disappear. Let's see. So I don't really need to liquefy it for the purposes of Charles Law. We're only talking about gas, it's not liquids here, but. It's really cool when it's a liquid, so I'm gonna show you that. And you can see that this is infinitely reversible as long as you've got lots of liquid nitrogen.
If you want to try this at home, you just blow up a balloon and put it in your freezer and see what happens. If you want to heat it up, maybe boil some water and hold it over the boiling water. Don't put it in the water, but like over the boiling. And see how temperature will affect that balloon.
So it's infinitely reversible. If I cool it, it shrinks. If I warm it, it should come right.
So that's how you can relate it. You can also relate it to your car tire, and things like that. So that's how you can kind of talk about volume and temperature. All right, so they're proportional. So as one goes up, the other will go up. The equation that Charles Law uses is V1 divided by T1 equals V2 divided by T2. You can keep your volume units consistent. They could be in milliliters or liters, but your temperature needs to be in Kelvin, always. So it'll be on several slides. Always convert your temperature into Kelvin. And we can qualitatively think about this. If I double my volume, what should happen to my temperature? It's double, they're proportional. If I half my volume, what should happen to my temperature? Half it. If I triple my temperature, what happens to the volume? If I decrease my volume by 1/4, what happens to temperature? Yeah, so the same concept here, and so qualitatively we can think about it, and then quantitatively we could also double check the math. So in this part, let's do this in two ways. A balloon has a volume of 4 liters. What will its new volume be if its absolute temperature is cut? So let's say the temperature is 100, and I half it by going from 100 to 50. What should happen to the volume? So what number should the volume be? It should be 2. If I half my temperature, no matter what number temperature I put, if I half it, my volume should also be half. So our answer should be 2 liters. If by knowing this, I was able to do this problem in 2 seconds. But the math will always back you up. So if you'd like to double check and make sure your math is correct, always do that, because that's what I do. V1 over T1 equals V2 over T2. So if I was to say V1 is 4 liters, and T1, it doesn't give us a temperature, but I can always make up my temperature. I can do 10, I could do 100, I could do 1,000, it doesn't matter. I'll do 100. But it needs to be in Kelvin. So if I half my temperature, 100 divided by 2 is 50. So V1, 4 liters divided by T1, 100, equals V2 divided by 50. So the way that this would work is you would, find that would be 4 out of 100, and then you multiply with 50 on both sides. So V2 should equal 2 liters, and then double check your math. So type this in your calculator and make sure you're able to get that number. So you can type this in your calculator by, 50 times and then in parentheses 4 divided by 100, or 50 times 4, which is 200 divided by 100. So that gives you 2. So yeah, the math will take you longer, but I'm a stickler where I'm like, okay, sometimes I just don't trust my brain, and that's okay. Math will always back me up. But if I don't have a lot of time, let's say this is an exam in any class, as long as I qualitatively can understand what's going on, I can eliminate and give myself a better shot if I don't know this equation. There is a significance of Charles' law because there's no such thing as a volume under 0. So as your temperature gets to very, very low temperatures, your volume can't really go negative. So you can see that as it approaches these very, very low temperatures of Kelvin, that it does slow down a lot. But in the opposite direction, if you increase your temperature, if you have the ability to have your volume increase a certain amount, it does get bigger. So I just wanted to point out that you can't have a negative volume. You can have negative temperatures, but not negative volume. Absolute 0 is the lowest temperature, the lowest possible temperature, and that's 0 degrees Kelvin or negative 273 degrees Celsius. I know under very specific conditions, maybe in a science lab, we can play around with other lower temperatures, but ideally, absolute 0 would be 0 degrees Kelvin. At this temperature, atomic molecular motion ceases, so gas particles halt. They're no longer freely floating. They're just halted. So quantum mechanical effects observed, such as superfluids and the Bose-Einstein condensate. So these are very, very special conditions. If you want to read up more about them, these two websites can explain it a little bit better. But there is a video, the very bottom one, that kind of shows you at absolute zero what is happening. This is at absolute zero.
In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cooled until a few degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops, and then the surface of liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particular is happening. Well, this is really one of the great phenomena in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an inlaid ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its containment. This is because the superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them.
That's what's showing what's happening at absolute.
It was hurting.
All right, so I'm gonna ask everyone to get that worksheet and just do the first page. So we're gonna stop maybe for like the next 10 minutes and do the first page of the worksheet. I got the key, okay. And then we'll come back. So for online, I'll put it up here, but it is available to you. So like number one says at room temperature, so I'm not gonna play around with the temperature, and 1 atmosphere, 2 moles of helium gas. So I'll just do like 2 pumps, 2 moles of helium gas are added to a balloon already. Okay, so they already have 2 moles. So if there's 2 pumps in here and I add 2 more pumps, okay. Raising the total number of moles of helium to 4 moles. Was the volume of the gas have double, tripled? So I needed to check what happens with volume. So I want to play around. So I'm keeping pressure to constant. So I already have 2 moles in here. And if I add 1, 2, what happened to the volume? So it increased based on what I did here. It increased, but I'm assuming it doubled. If you, whatever you do to the amount, it should also double the volume. That's because more collisions, they want to expand. All right, number 2, a chamber with a movable top contains the movable top. Okay. Contains 6 moles of gas. I'll just put 6 moles. 1, 2, 3, 4, 5, 6. Okay, so it decreases the volume by half. Oh, wait. I half the volume. What happened to the pressure? So at normal pressure, and then I half the pressure. Or, yeah, sorry, I half the volume. The pressure should do the exact opposite. So if I half the volume, I should double my pressure. No. That's pretty much the same. So if this pressure is 36.36, very similar. So I double my pressure. Yeah. Okay. So let's move on to the second part of the slides. We're not going to finish it. Obviously, we only have 7 more minutes, but I want to get as much as I can done because we're going to start connecting all the dots using 2 new equations, and we're going to have to go back to using verse. So gas laws and verse. As we switch now to quantitative gas laws, so now we're going to actually use numbers using all these equations. We still want to think qualitatively to make sure our numbers make sense, our overall evaluate, but we're going to be doing a little bit more difficult problems. So we're going to use our verse skills to solve these word problems, and we were going to be using 2 different equations for this. The ideal gas law, which you've already seen, so that's PV equals nRT, and combined gas law. P1 V1 over T1 equals P2 V2 over T2. So this equation here is just a combination of Charles' law and Boyle's law. It's just we've already kind of seen it, where P1 V1 equals P2 V2, and then V1 over T1 equals V2 over T. So you have to be able to like use or know when to use each equation. So I'll tell you now. The ideal gas law, the equation on the left, you're only going to use it when they give you 1 pressure, 1 volume, 1 mole, 1 temperature. The equation on the right, you use when you're given 2 of something. So you might be given 2 pressures or 2 volumes or 2 temperatures. So that's how you can decide when to use what equation. So here's that equation again. You can use any unit for pressure for this combined gas law. And that's only for this one because the ideal gas law has to be in atmospheres. But this one can be in torr. It could be in millimeters per mercury. It can be consistent. Same with the volume. It could be consistent as long as the units are consistent. And then use the before as, or the original or the initial is going to be the 1s. The after will be the 2s. So it could be initial and final. It could be before and after. Use the words of the problem to decide is it a 1 or a 2. But temperature needs to always be in Kelvin. So I want to point out that kind of using what we discussed before, sometimes with these problems, they might say, okay, I'm changing my volume and I'm changing my temperature, but I'm not changing my pressure. If, let's say, pressure is equal to 1 atmosphere for both before and after. So sometimes they'll say this is being held constant. You can go into this ideal or this combined gas law equation and just take out the pressure. They'll cancel each other out in the end. So instead of you incorporating it into the problem, which you can, you'll get the right answer anyway. You could just take it out and be left with what's left. If I was, say, at constant temperature, let's say it's at room temperature, you just go in and take out those and continue on. So you can either do it before or after. The math will always give you the right answer if I was to say a number, but sometimes they just don't give you a number. You can either come up with a number or you can just don't include it in this problem. Simply cancels out of the equation. Even if you don't know the numeric value, don't include it if it's constant. For the ideal gas law equation, you've already done this when we were doing verse the first time. So PV equals nRT. This equation is used when you're given only 1 pressure, 1 volume, 1 temperature, 1 amount. So R is the ideal gas law constant. That's what we've given to you. The units of R are liter atmospheres divided by mole Kelvin, which means your pressure needs to always be in atmospheres. Your volume needs to always be in liters. your amount needs to always be in moles and your temperature needs to always be in Kelvin. So for this equation to always be successful, you have to use those conversions. And if you ever forget which one of those conversions are, look at the units of R. R tells you what units you have to have. So we need to be able to decide which equation to use in the following problems. So just remember, if it has one set of parameters, we use ideal gas law. If you have two sets of parameters, like two temperatures, you'll have to use the other one, the combined gas law. I think we have time to practice one. So this one says a gas sample at 273 Kelvin has a volume of 2.5 liters. So verse, I'm going to write out these variables. So this one looks like I have a T1 equals 273, a V1 equals 2.5 liters. At what temperature, which means I do not have a second temperature, would the sample be if I have a volume of 7.5 liters? That's P1 V1 over T1, P1 2V2 over T2. They don't mention pressure here. So I can assume pressure is being held constant, which means I get to just take this equation and just remove the pressure. So that's Charles' law. We've already done Charles' law. So 2.5 liters divided by 273 Kelvin equals 7.5 liters over question mark. So go ahead and solve what that question mark should be. And once we have that, the class will be over. You can also kind of check your math by knowing, okay, if pressure and, volume and temperature are proportional. So if I increase my volume going from 2.5 to 7.5, my temperature should also increase. So I got T2 equals 819 Kelvin. So that makes sense. My temperature should also increase. So that's all I have for today. We'll do the last 4 problems together next class on Wednesday, and then we'll move on to the next section. But I'll make sure I have that page up ready to go for you to download. Yeah. If y'all have any questions or need to, I haven't given your exam back, please, I'll give it to you. And I promise I'll have the first homework up today, so you can start working through it if you want over the next couple days.